the shore. And so there was 18 meters of water, 18 meters of very soft alluvial clay, and several hundred meters of Pleistocene clays. These Pleistocene clays are alternating with sand layers, which are more or less draining. So that's the situation, which is quite complex due to these sand layers, which are more or less draining. And so, for building the island, in fact, the alluvial clay has been treated with vertical drains, and in fact, the settlement of alluvial clays was completed in about 6 months. So the long-term settlements are coming from the Pleistocene clays. In fact, Professor Akai calculated settlements on the basis of 24 hours de Meter test and neglecting viscosity or rate effects. He came with a final settlement of 5.9 meters. And here you have the field observations. And in 1994, when the airport was opened, in fact, the calculated settlement was equal to the measured one. So everything was apparently going well. But then you can see that the field settlements are much more important than the predicted one. And the 5.89 meters was reached in 1998. And in 2002, the settlement was 1 meter larger. And in fact, when we look at the pore pressures under the embankment, under the island, in fact, we can see that in this period, the excess pore pressures are still larger than 200 kPa. That's a lot of pore pressures to dissipate, which means that there is still a lot of settlements to come. So, and we think that is consistent with the rate effect observed on Osaka Bay clay, with the result shown here. And we said, in fact, with David Height, that in fact it's another proof that hypothesis A is wrong. We must say, however, that Mesri and Funk last year published a paper analyzing the Kansai airport case, and consider that the end of primary settlement would be of about 9 meters rather than 5.9 meters calculated by Akai, and that hypothesis could be correct. I must say that I doubt about these results. Okay, so there is no doubt in my mind that there is creep during primary consolidation and that hypothesis A is incorrect. Now, what do we do practically to calculate settlements? And my conclusions that I got about 10 years ago are the following. In high compressibility clays, or in cases of well-controlled embankments, or in cases where excessive settlements may have important consequences, viscous effects must be considered during primary consolidation. There are several approaches which can be followed. One is numerical modeling, and there are several models on the market, or add a viscous component called delta epsilon field to the strain calculated on the basis of the 24 hours compression curves. In fact, there are three main questions. The first one is, what is the in situ sigma prime P or sigma prime Vy? And what is delta epsilon field that we would have to add to the strain calculated on the basis of the 24 hours compression curves? And the third question is, what is the representative coefficient of consolidation? About the first question, in fact, we compared sigma prime Vy in the field with sigma prime Vy obtained after 24 hours, and we obtained a good agreement for OCRs lower than 2.5. For OCRs larger than 2.5, in fact, the field data are smaller, and this has been explained by the shape of the limit state curves of natural clays. That means also if you change your 24 hours pre-consolidation pressure by pre-consolidation pressure obtained at larger strain rates, as in CRS test, at that time you could underestimate the pre-consolidation pressure and the settlement. So be careful. Now about delta epsilon field, it has been calculated by Watabe, on the basis of data from Watabe et al. And published with Watabe and myself in 2013. The figure on the left gave the delta epsilon ultimate, because we know there is an ultimate value, versus C sub C over 1 plus E0. And you could examine this to see if delta epsilon field is important or not. If you want more accurate value and more practical one, here is a delta epsilon field versus the strain rate in the field. And for example, for VSB, the viscous strain to add to the settlement calculated on the basis of the 24 hours odometer curves will be of about 6%. Now for normal practice, everyday practice, low compressibility clays, because there are several factors which are, say, fighting against the viscous effects. I mentioned the effect of strain rate first in low compressibility clays is relatively small, but in most cases, in normal practice, we have sampling disturbance. Settlements imply a decrease of the applied total stress with time that is often neglected. Quite often, the water table rises in the embankment, and the 24 hours odometer test already includes some secondary compression. All these factors are to some extent compensating for the viscous effects. So my conclusion is that the the rate effects on settlements during primary consolidation are to some extent compensated and can be neglected when 24 hours compression curve is used in the calculation. So, in conclusion, from now on, do as you have done before, except for special cases. Consolidation. In fact, because CV is high in the over-consolidated domain, the vertical yield stress is generally reached during construction. That means that at the end of construction, generally, the vertical effective stress is on the pre-consolidation pressure profile, which means that on the long term, the pore pressure to dissipate is the one which is shown in green here, in the normally consolidated range, which means that the relevant coefficient of consolidation is the one in the normally consolidated range. From our experience in Eastern Canada, with several sites and several embankments, what happens is that for under embankments, the normally consolidated coefficient of consolidation is typically around 10⁻⁷ square meters per second. In the over-consolidated range, it's typically, I would say, 50 times larger, because in the over-consolidated range, the natural clays are quite stiff. Now, if we consider the CV values obtained in odometer tests and analyzed with the log-T method, the CV underestimates the real value in situ, and typically for our clays by a factor of 10, which is significant. Now about the CV defined with the piezo cone. In fact, it appears that it's somewhere in between, in fact, right in the middle between the the C sub V in the over-consolidated range and the C sub Z in the normally consolidated range. And this has been demonstrated by Fae and LIGO that it's just logical to have this CV between the over-consolidated one and the normally consolidated one. However, as far as embankments is concerned, from experience, it's just useless. Now, main conclusions. In fact, the compressibility of clay soils is controlled by strain rate and also temperature. Isotac hypothesis B provide a consistent constitutive model which applies during both primary and secondary consolidations, and all well-documented cases support its validity. Hypothesis A is incorrect and requires two constitutive equations, one during primary consolidation and another one during secondary consolidation, which is certainly not logical. As demonstrated with the VSB case, it may provide reasonable results when samples are sufficiently disturbed. So, thank you very much for your attention.